Good evening, and thank you for joining me for another Boring Books for Bedtime. I hope tonight's selection provides all the boredom your busy brain needs to quiet down and let you get some sleep. Before we begin, I'd like to give a special shout out of thanks to some new members of our Patreon family: Mary, Martin, Shelley, Jenny, and Stephen, Svaya, and Henry. Thank you all so much for supporting this podcast. By becoming members of Patreon, you help us remain 100% listener-supported and ad-free for everyone, and it's very much appreciated. If you're interested in supporting Boring Books for Bedtime and finding out more about the perks available to subscribers, including exclusive episodes, fictional readings, and full books found nowhere else, you'll find a link to Patreon in the show description. You'll also find a link to buymeacoffee.com, where you can support us with a one-time tip, no subscription required. I hope you'll take a moment to check them out. Now, let's read and relax. Find a comfortable spot. Adjust your volume. Take a nice deep breath in. Let it out slowly. And off we go. Tonight, we reach the conclusion of a book I've really enjoyed reading on this podcast: Astronomy for Young Folks by Isabel Martin Lewis, A.M., connected with the Nautical Almanac Office of the U.S. Naval Observatory. Copyright 1921 by the Century Company and 1922 by Duffield and Company, New York. Let's pick up right where we left off at chapter 29. Let's begin. Chapter 29, Double and Multiple Stars. The plan of the solar system, which consists of a central sun encircled by satellites that are far inferior to their luminary in size, and that move about it in orbits that are almost perfect circles, is not the only, nor possibly even the most general one in the universe. Sweeping the heavens with powerful telescopes, one is astonished to find that myriads of stars can be separated into two or more physically connected suns that are often, moreover, of exquisitely tinted and contrasting shades: green and red, orange and white, white and golden, or white and blue pairs exist in profusion, and strange to say, there are well-authenticated instances of color changes taking place temporarily within the same system. A pair of white stars has been known to change within a few decades, first to golden yellow and bluish green, and then to orange and green. The famous pair catalogued as 95 Hercules was noted to change from green and red to a palish yellow and back to the original strongly contrasting hues within the course of a single year, while at another time they appear to be a perfectly white pair. At the present time, both of these stars are decidedly yellowish in color. Such changes in hue are probably due to temporary disturbances in the atmospheres of the stars, possibly of an electrical nature, or to sudden or unusual outbursts of activity, concerning the origin of which we are as much in doubt as we are of the cause of the sunspot cycle and periodic variation in the intensity of radiation of our own sun. Temporary changes in the color of the components of double star systems sometimes take place when the two stars approach their periastron, or point of nearest approach. Owing to the great eccentricity of the orbits of double stars, such stars are anywhere from twice to 19 times as near to each other at periastron as they are at apastron, or point of greatest departure. Such great changes in the relative distances of two physically connected suns would produce marked changes in the intensity of the tides raised upon each of them by their mutual gravitational attraction, and unusual outbursts of gases or electrical excitement in the atmospheres of the stars might cause very noticeable changes in the color of these stars as they drew nearer to each other, which would subside as they receded toward apastron. In addition to visual double or multiple stars, there exists a very extensive class of stars known as spectroscopic binaries, in which the two components are so close to each other that even the most powerful telescopes cannot divide them. It is only from the shifting of the lines of their overlapping spectra, caused by their alternate motion toward and from the Earth as they revolve about their common center of gravity, that their duplex nature is revealed to us. In some instances, one member of the system is so faint that its spectrum is not visible, and its presence is disclosed only by the shifting of the lines of the bright star. According to Doppler's law, when a star is approaching the Earth, the lines of its spectrum shift toward the blue end of the spectrum, and when the star is receding from the Earth, the lines are shifted toward the red end of the spectrum. The amount of this shift can be very accurately measured and gives the relative velocities of the stars in their orbits directly in miles per second. Knowing in addition, by observation, the period of mutual revolution of the stars, it is possible to find the dimensions of these spectroscopic binary systems compared to our own solar system, and also the masses of the stars compared to the mass of our own sun. If the spectrum of the fainter star is not visible, only the velocity of the brighter star with respect to the center of gravity of the system can be found, and the mass found for the system comes out too small. In such cases, we can obtain only a lower limit for the mass of the system. Then, too, it must be remembered that these systems of stars lie at all angles with reference to our line of sight, and so we rarely see the orbits in their true form. The measured velocities are as a result smaller than the true velocities, and on the average amount to only 60% of the true orbital velocities. The calculated masses of spectroscopic binary stars are, therefore, in general, only about 60% of the true masses. It has been found from calculating the masses of a number of binary systems that the combined masses of the stars in these systems do not differ very greatly among themselves, nor as compared to our own sun, though in light-giving power these stars may differ hundreds, thousands, even millions of times. For instance, there are stars that give only 1/10,000th part of the light of our own sun, and other stars that give 10,000 times as much light as the sun. Moreover, there are many instances of physically connected stars differing thousands of times in luminosity, though in mass, or quantity of matter found in the stars, they differ only 2 or 3 times. Why this is so remains one of the great mysteries of the heavens and makes it extremely difficult to give any satisfactory theory of the origin of double star systems. It has never been explained satisfactorily why, of two suns physically connected and therefore presumably originating at the same time, one should be radiating with the greatest intensity, while the other is practically an extinct sun, in spite of the fact that the quantity of matter in the two bodies differs but slightly. In a few systems, the plane in which the stars revolve passes so nearly through the Earth that the two stars temporarily eclipse one another during each revolution. Such systems are called eclipsing binaries. To such a system belongs the famous Algol. Its light waxes and wanes periodically with the greatest punctuality in a period of 2 days, 20 hours, 48.9 minutes, owing to its temporary eclipse by a very large but extremely faint attendant sun. The diameter of the faint star is slightly greater than the diameter of the bright star, which is about 1,000,000 miles in extent. The distance between the centers of the stars is only about 3,000,000 miles, which brings their surfaces within 2,000,000 miles of each other. The masses of the two stars are in the ratio of 2 to 1, the brighter and more massive star being about half as heavy as our own sun, though its density is only about 2/10 that of the sun. The density of the fainter star is still less, being only about half that of the brighter star. Very low density of both components and extreme faintness of one member compared to the other appears to be a very general characteristic of closely associated eclipsing and spectroscopic binary stars. Among the extremely hot and brilliant helium and hydrogen stars, spectroscopic binaries exist in great numbers. In fact, among these types, there appear to be as many binary and multiple systems as there are systems of isolated suns. Sometimes these close binary stars are egg-shaped or oval and revolve rapidly, almost in contact, about their common center of gravity. Inhabitants of satellites of such a system would see in their heavens the, to us, strange and startling phenomenon of two suns, each equal to our own or even greater in size, whirling rapidly about each other and separated by a space comparable in extent to their own diameters. Eclipses in such a system would be of daily occurrence, and if one star were dark, would produce for the satellite world the same effect of alternate day and night that results from axial rotation of a satellite. The two hemispheres of the faint companion sun would be very unequally illuminated, owing to the fact that the side turned toward the brilliant sun would always reflect its neighbor's brightness, in addition to shining with its own comparatively feeble inherent light, while the opposite hemisphere would shine only by its own dim light, and would, therefore, be in comparative darkness. The spectroscopic binaries generally revolve closely and rapidly about their common center of gravity. There are to be found, on the other hand, among the wider visual doubles, many systems wherein the components are separated by distances comparable to the distances of the outer planets, Saturn, Uranus, and Neptune, from the Sun. It is evident that the individual stars of such binary systems could not possibly be encircled by any such extensive system of satellites as attends our own Sun, though satellites such as our own planet Earth or the inferior planets Mercury and Venus might conceivably encircle the individual components of such binary systems at distances not greater than that of the Earth from the Sun. No planet could safely exist at a much greater distance from one of these suns without being subject to most dangerous perturbations and disruptive tidal forces arising from the vicinity of the second sun. Granted that planets might encircle one of these suns at a distance approximating that of Venus or our own planet from the Sun, the inhabitants of such worlds would behold this strange phenomenon of two suns in the heavens, not almost in contact, as in spectroscopic binary systems, but at one time comparatively near, and again in opposite portions of the heavens, as is the case with the sun and moon in our own heavens. As the planet advanced in its orbit about the ruling sun, the secondary sun would be visible at first by day and again by night. If the two suns were of contrasting hues, as for instance green and red, there might appear in the nearby heavens at a distance of 100 million miles or so, a magnificent sun of deep reddish hue, equal to or surpassing our own in splendor, while in a far distant part of the sky, at a distance as great as that which separates us from the planet Saturn, might appear a rival sun of greenish hue, smaller and fainter, but nevertheless hot and extremely brilliant, and capable of exerting through its great gravitational attraction a most disturbing effect upon the motion of the planet of its neighbor. At times, the rays of the two suns, red and green, would combine to produce a day characterized by terrific heat and intense illumination. Again, the green orb would rise in the east as the red sun set in the west, and night would be turned into a weird, dimly lighted day by the greenish rays of the secondary sun. Compared to the wonders and beauties of the heavens in such a system, our own well-regulated and orderly planet family, undisturbed by the exciting proximity of a rival sun, seems to pale into insignificance. Yet we have every good reason to be content with the ordering of affairs within our own solar system, and to feel relief rather than regret at the absence of a secondary sun. In a planet world revolving about one member of a double star system, we may imagine the dread rather than pleasure with which the periodic near approach of a rival sun would be hailed, and even the possible hurried migration from exposed to sheltered portions of the planetary world to escape the rapidly increasing heat and intensity of light from the approaching sun. In such systems, the coming and going of the seasons might indeed be a matter of life and death to the inhabitants of satellite worlds. Within our solar system, the masses of the planets are practically negligible compared to the mass of the sun, and it is for this reason that they appear to revolve about the center of the sun. As a matter of fact, no body in the universe revolves about the exact geometrical center of another body, but two mutually attracting bodies revolve in orbits about their common center of gravity, which always lies between the two bodies on the line connecting them and at a distance from each of them that is in inverse proportion to the mass of the body. the moon does not revolve about the center of the earth, but about the center of gravity of the earth and moon, which lies on the line connecting the two bodies, and at a distance from the earth's center that is 1/81st of the distance from the center of the earth to the center of the moon, since this represents the ratio of the masses of the two bodies. This center of gravity of the earth and moon lies, then, about 2,000 miles from the earth's center, and about this point both earth and moon trace out orbits of revolution that are identical in form and differ only in size. In the same way, each of the planets of the solar system revolves around the center of gravity of itself and the Sun, but the mass of the Sun is so far in excess of the combined masses of all the planets that we may consider, for all practical purposes, that the planets revolve about the Sun's center, the center of gravity of the system being within the Sun, just as the center of gravity of the Earth and Moon is within the Earth. Professor T.J.C. found from the investigation of 40 binary star orbits that the average eccentricity of double star orbits is 12 times as great as the average eccentricity of a planetary orbit, and that the masses of the component suns never differ very greatly. The center of gravity of a binary system, therefore, lies at a great distance from the centers of the stars, and about this point, as a focus, the stars move in orbits that are exactly similar in form, but differ in size in inverse proportion to the ratio of the masses. Since the orbits of binaries are, moreover, very highly eccentric, the two suns are, as we have said, anywhere from 2 to 19 times nearer to each other at periastron than they are at apastron. We have spoken so far only of systems of two associated suns, but many systems exist in which 3 or more sun-like bodies are in revolution about a common center of gravity. Frequently, 2 fairly close suns are in revolution about a common center of gravity in a period, say, of 50 or 60 years, while a third sun revolves at a comparatively great distance about the center of gravity of itself and the first pair in a period of several hundred years. Or possibly, the third sun also possesses a close attendant, and the 2 pairs revolve in a period of great length about a common center of gravity. Such, for instance, are the systems of Zeta Cancri and Epsilon Lyrae. In the former system, the closer components revolve rapidly about their center of gravity in a period of about 60 years, while the remote companion shows irregularities in its motion that indicate that it is revolving about a dark body in a period of 17.5 years, while the 2 together are revolving very slowly in a period of 6 or 7 centuries about a common center of gravity, with the first pair in a retrograde direction. The wider pair of Epsilon Lyrae is a naked eye double, for it can be seen as a double star by a keen eye, while even a 3-inch telescope will separate each of the components into a double star. So extensive is this system that the periods of revolution of the closer components occupy several centuries, one pair appearing to revolve about twice as rapidly as the other, while the period of revolution of the 2 pairs about a common center is probably a matter of thousands of years. The gap that separates the 2 pairs may be so great that light requires months to cross it. These multiple systems are by no means exceptional. They are to be found in profusion among the brilliant Orion stars. They have been referred to as knots of stars, and it has been suggested that they may have originated as local condensations in one vast nebulous tract. A system of only two components appears to be the exception rather than the rule, groups of several connected suns being more numerous than single pairs. In all of these double and multiple systems, there exists the possibility of minute satellites, such as our own Earth, in attendance upon some one component of the system. Such tiny bodies, shining only by reflected light from a nearby brilliant sun, would be hopelessly invisible in the most powerful telescope. We can only assume that it is far more reasonable to believe in than to disprove the existence of such satellites. Our own solar system, then, represents neither in its mechanical nor physical features the only possibilities for the maintenance of life. It can neither be considered a unique form nor even the most generally prevalent form in the universe. Chapter 30: Astronomical Distances. The grandeur of the scale upon which the visible universe is fashioned lies almost beyond human comprehension. In measuring the vast extent of our own solar system, which is but a single unit in the system of the stars, we may have recourse to some earthly standard of measurement, such as the mile. But when we desire to express in terms of units that can be grasped by our imagination the distances of the stars that lie far, far beyond, we find that all ordinary standards of measurement become utterly inadequate for our purpose. In the measurement of celestial distances within the solar system, the unit employed is either the familiar mile or kilometer, or the astronomical unit, which is the mean distance from the Earth to the Sun, 92,900,000 miles in round numbers. In the measurement of distances beyond the solar system, the unit employed is either the light year, or more recently, the parsec, which is rapidly replacing the light year among astronomers. A light year is the distance that light, with its finite but almost unimaginable velocity of 186,000 miles per second, travels in a year. It is equal in round numbers to 63,000 times the distance from the Earth to the Sun, or approximately 6,000 billions of miles. The parsec is equal to 3 26/100, 3.26 light years, and it is approximately 200,000 times the distance from the Earth to the Sun. It is the distance of a star with the parallax of a second, a fact which its name, parsec, conveys to us. In other words, at the distance of 1 parsec, the distance from the Earth to the Sun, the astronomical unit, would subtend an angle equal to 1 second of an arc. This angle is spoken of as the parallax of the star. The larger the parallax, that is, the larger the angle the astronomical unit or radius of the Earth's orbit subtends viewed from the star, the nearer the star is to us. The fact that there is no known star within 1 parsec, or 3 26/100 light years of the Sun, shows the immensity of the scale of the universe of stars. Before considering the distances of the stars and the extent of the sidereal system of which our Sun and his satellites form a part, let us undertake to express the distance of the Sun, Moon, and planets from the Earth, and the extent of the solar system in terms with which we are familiar. The nearest to the Earth of all celestial bodies is its satellite, the Moon. So near is the Moon that if we should make on some great plain a model of the solar system, in which the astronomical unit, the distance from Earth to Sun, would be 400 feet, the distance between the Earth and Moon would be only 1 foot. On the same scale, the most distant planet Neptune would be 2 1/4 miles away. Granted that it were possible to escape the Earth's gravitational bonds and to travel by our swiftest means of conveyance, the airplane, through interplanetary space, let us consider how long it would take us to reach the Moon, Sun, and planets if our speed were maintained at a uniform rate of 200 miles an hour. An airplane traveling at this rate would circumnavigate the Earth in a little over 5 days and would reach the Moon in 7 weeks. A trip to the Sun, however, would take 53 years. After traveling for 14 and a fraction years, we would pass the orbit of Venus, and 18 years later, the orbit of Mercury. If we prefer to travel outward from the Earth in the direction of Mars and the outer planets instead of toward the Sun, more than 27 years would elapse before we would reach the orbit of Mars. An airplane journey to Jupiter would be a matter of more than 200 years. To Saturn, 450 years. To Uranus, nearly 1,000 years, and to Neptune, about 1,500 years. To cross the solar system on the diameter of Neptune's orbit in an airplane, traveling day and night without stopping at the rate of 200 miles per hour, would take more than 3,000 years. The Sun's attraction reaches far beyond Neptune's orbit, however. There are comets belonging to the solar system, compelled by the Sun's attraction to accompany him on his travels through space, that return periodically to the immediate vicinity of the Sun from regions far beyond the orbit of Neptune. And there is also the possibility that one or more undiscovered planets may travel around the Sun in orbits far exterior to Neptune's orbit. Measured in terms of familiar units, such as are employed for the measurements of distances on our own planet, the extent of the solar system is tremendously great. Viewed from Neptune, the Sun is so far away that it presents no appreciable disk. It is in this sense star-like to the Neptunians, but at the distance of Neptune, the stars appear no more brilliant and no nearer than they do to us. To Neptune, the Sun, though star-like in form, supplies a very appreciable quantity of light and heat, 1/900th of the amount the Earth receives, while the amount of light and heat that Neptune receives from the nearest stars is entirely inappreciable. When our airplane reaches Neptune after a journey of 1,500 years, it is, as it were, just clearing the ground for its flight to the stars. To cover the intervening space to the nearest star, traveled by light in 4 1/3 years, an airplane would need 14.5 million years. In that time, the solar system itself would be in some far distant part of the universe, since it is speeding onward through space at the rate of 12 miles a second, or about 4 astronomical units a year. Changing now our unit of measurement that we may express interstellar distances in comprehensible numbers, we prepare to travel from the Earth to the stars with the velocity of light. With this velocity, 186,000 miles per second, we circumnavigate our globe in 1/7 of a second, reach the moon in 1 1/4 seconds, and the sun in 8 minutes. In a little over 4 hours, we pass the orbit of Neptune and are started on our journey to the stars, penetrating further and further into interstellar space. For a year, we travel and reach not a single star, though we are speeding ever onward with the velocity of light. We have now covered the distance of 1 light year, which means that the waves of light from the sun we have left behind must travel for a year before they reach us. We continue our journey and find ourselves next at a distance of 1 parsec from the sun. We have traveled a distance of approximately 3 1/4 light years, and were it possible to see the Earth as well as the sun at this distance, the two would appear to be but 1 second of arc apart, a distance that requires the most careful adjustment and manipulation of the telescope to measure accurately. We are still 1 light year distant from Alpha Centauri, the nearest of the bright stars. A few of the stars will now appear somewhat brighter than they appear to us on Earth, but the majority of the stars appear just as we see them here, and the forms of the constellations remain practically unchanged in appearance, for we are only beginning our journey through the sidereal universe, and our position in it has only shifted by a very slight amount. If we should continue our journey to the immediate vicinity of Alpha Centauri, we would find that it is not like our own sun, a single star, but is a binary star consisting of 2 suns in revolution about their common center of gravity. The distance of this binary system from the solar system has been measured with considerable accuracy and is known to be 4 1/3 light years. Though there may be a few faint stars or non-luminous stars nearer to us than Alpha Centauri, this star has long held the distinction of being the nearest of the stars. As the sun continues his journey through the universe, the 2 stars, Alpha Centauri and our sun, will finally draw away from each other after many ages have passed, and some other sun of space will be our nearest star. The distances that separate the stars from each other probably average as great as the distance from the sun to Alpha Centauri. Within a sphere whose center is at the Earth and whose radius is 5 parsecs, or about 16 light years, there are only about 20 known stars. There is therefore small chance of collision among bodies that are so small in proportion to the tremendous intervals of space that separate them from each other. There is ample room for the individual stars to pursue their journey through space without interfering with each other's motion, so long as they are as widely scattered as they appear to be in this portion of the universe. The fact that our own sun has continued its journey through the universe for some hundreds of millions of years without any catastrophe, such as would result from closely approaching or colliding with another sun of space, shows how enormous is the scale upon which our sidereal system is fashioned. Stars that are 10, 50, or even 100 light years from the Earth are our nearest neighbors in space. They are the stars that show a slight displacement in the heavens or measurable parallax, viewed from opposite sides of the Earth's orbit. There are probably 1,000 stars among the hundreds of millions of stars within reach of the greatest telescopes, whose distances have been determined in light years by direct measurement of their displacement in the heavens, resulting from the change of position of the Earth in its orbit. The most distant of the stars are apparently immovable in the heavens, showing neither the effect of the sun's motion or their own motion through space. Methods for finding the distances of many far remote stars and star clusters have been devised, however, and some comparatively recent investigations have given results for the distances of these objects indicating that the diameter of the system of stars to which our Sun belongs is approximately 300,000 light years. It is difficult to grasp the full significance of this fact. It means that hundreds of millions of the suns of space throng the visible universe at distances from us and from each other, running into hundreds, thousands, and even hundreds of thousands of light years. The light waves from some tiny object that we view today in one of our great reflectors may have started on their journey through space over 100,000 years ago, when men of the old Stone Age inhabited our planet Earth. Astronomers have found, as a result of their investigations, that the sidereal system to which our solar system belongs is in the form of a flattened spheroid with its longest axis in the plane of the Milky Way. The extent of this star system, composed of hundreds of millions of individual suns, in addition to nebulae and clusters, is probably something like 300,000 light years along its longest axis, while globular star clusters lying above and below its central plane are estimated to be at distances from it ranging from 10,000 to 200,000 light years. This entire organized system is our sidereal universe. Space beyond is unexplored. The globular star clusters are among the most distant celestial objects so far discovered. The spiral nebulae may be entirely within the limits of this system, or they may be even more distant than the globular clusters, for their distances are not known as yet. There is a possibility that our sidereal universe, vast as it is known to be, may be but a unit in some still greater unit, and that other similar systems lie beyond the reach of existing telescopes at unimaginable distances. The mind of man is overwhelmed by the thought of sidereal systems as vast as our own, lying far beyond his ken. Whether or not such external systems do exist and are with our own sidereal system, units in still some vaster creation, we cannot know. So vast indeed is this one visible universe of ours, that the mind of man, accustomed to earthly standards, cannot comprehend its magnitude or the infinitesimal size of our whole solar system compared to it. Chapter 31. Some Astronomical Facts Worth Remembering. Kepler's 3 Laws of Planetary Motion. 1. The planets move in ellipses with the Sun at one focus. 2. The radius vector of a planet, the line adjoining the Sun and planet, sweeps over equal areas in equal times. 3. The square of the time of revolution, the year of each planet, is proportional to the cube of its mean distance from the Sun. Sir Isaac Newton discovered that the law of gravitation extends to the stars. That is, every mass in the universe attracts every other mass, with an attraction directly proportional to the product of the masses and inversely proportional to the square of the distances between them. Ocean tides are caused by the difference between the attraction of the Sun and Moon for the main body of the Earth and their attraction for different particles of the Earth's surface. The tide-raising force of the disturbing body is proportional to its mass and inversely proportional to the cube of its distance. The tides produced by the Sun are, therefore, only 2/5 as great as the tides produced by the Moon. The celestial sphere is an imaginary sphere of infinite radius, with the Earth at its center, upon which the celestial bodies are considered to be projected for convenience in determining their positions with respect to fixed points of reference in the heavens. The north and south poles of the heavens are the points on the celestial sphere directly above the north and south poles of the Earth. The celestial equator is the great circle in which the plane of the Earth's equator intersects the celestial sphere. It passes through the east and west points of the horizon and through the zenith, or point directly overhead at the Earth's equator. The ecliptic is the great circle in which the plane of the Earth's orbit intersects the celestial sphere. The celestial equator and the ecliptic are inclined to each other at an angle of 23 1/2 degrees, which is called the obliquity of the ecliptic. The 2 points in which the celestial equator and the ecliptic intersect are called respectively the vernal equinox and the autumnal equinox. The vernal equinox is an important point of reference on the celestial sphere. As the position of a point on the Earth's surface is determined by its longitude and latitude, so the position of an object on the celestial sphere, star, sun, planet, is determined by its right ascension and declination. The declination of a celestial object is its distance north or south of the celestial equator measured in degrees, minutes, and seconds of arc on a great circle of the celestial sphere, passing through the object and north and south poles of the heavens. These great circles are called hour circles, and they correspond to the meridians or circles of longitude on the Earth's surface. The declination of an object in the heavens corresponds to the latitude of a point on the Earth's surface. The right ascension of a point on the celestial sphere corresponds to the longitude of a point on the Earth's surface. It is measured as longitude is measured, in degrees, minutes, and seconds of arc, or in hours, minutes, and seconds of time, eastward along the celestial equator, from the hour circle passing through the vernal equinox to the foot of the hour circle passing through the object. The hour circle passing through the vernal equinox is the zero meridian for the celestial sphere, just as the meridian of Greenwich is the zero meridian on the Earth's surface. The mean distance of the Earth from the Sun is 92,900,000 miles and is called the astronomical unit. The Sun, with its satellites, advances through the universe at the rate of 4 astronomical units in a year, or approximately 1 million miles a day. The parallax of a star is the angle at the star subtended by the radius of the Earth's orbit, 92,900 miles, or the astronomical unit. It is, in other words, the angular distance between the Earth and Sun as viewed from the star. The larger the parallax, the nearer the star. The largest known stellar parallax is that of Alpha Centauri. The light year is the distance that light travels in 1 year. It is equal to about 63,000 astronomical units, or nearly 6 trillion miles. The velocity of light is 186,000 miles per second. The parsec is equal to 3.26 light years. It is the distance of a star that has a parallax of 1 second of arc. The apparent magnitude of a star is its apparent brightness, estimated on a scale in which a difference of 1 magnitude corresponds to a difference in brightness of 2.51, or the 5th root of 100. A difference of 5 magnitudes corresponds to a difference 1/100-fold in brightness, of 10 magnitudes to 10,000-fold in brightness. In exact measurements on this scale, magnitudes are estimated to tenths. Stars that are 1 magnitude brighter than stars of the standard 1st magnitude are of the 0 magnitude, and stars still brighter are of negative magnitudes. Sirius is a star of the negative 1.6 magnitude. Jupiter at opposition is of negative 2.0 magnitude, and Venus at greatest brilliancy of negative 4.0 magnitude. The Sun on this scale of comparative brightness is of the negative 26.7 apparent magnitude. The faintest stars visible in the most powerful telescope in the world, the 101-inch Mount Wilson Hooker telescope, are of the 20th magnitude. The absolute magnitude of a star is its apparent magnitude at the standard distance of 10 parsecs, or 32.6 light years. The absolute magnitude of the Sun is 5. That is, the Sun would be a 5th magnitude star at the standard distance of 32.6 light years. The absolute magnitudes of stars indicate how bright they would be, relatively, if they were all at the same standard distance. Apparent magnitudes indicate how bright the stars appear to be at their true distance. The mean distance of the Moon from the Earth is approximately 240,000 miles, or 60 times the Earth's radius. The Sun is 400 times farther away than the Moon, and its diameter is about 400 times greater than the Moon's diameter. The nearest star is about 275,000 times more distant than the Sun. And the most distant known object, the globular star cluster NGC 7106, is about 14 billion times more distant than the Sun. The Earth is a spheroid flattened at the poles, and its polar diameter is about 27 miles shorter than its equatorial diameter. An object weighs less at the poles than at the equator. The Earth's interior is as rigid as steel and probably consists of a core of magnetic iron surrounded by an outer stony shell. Eclipses of the Sun occur when the Moon passes between the Earth and the Sun. They can only occur at the time of new moon. There must be at least 2 solar eclipses every year, separated by an interval of 6 months, and there may be as many as 5 solar eclipses in a year. Eclipses of the moon occur when the Earth comes between the sun and moon, and the moon passes into the Earth's shadow. Eclipses of the moon can only occur at full moon. There may or may not be eclipses of the moon every year. The greatest number of eclipses that can occur in any one year, solar and lunar combined, is 7, and the least number is 2, and in that case they are both solar eclipses. The Sun is a yellow dwarf star of a density of 1 1/4 that of water, and with a surface temperature of about 12,000 degrees Fahrenheit, except in sunspot regions, where the temperature is about 6,000 degrees Fahrenheit. It is probably gaseous throughout. The Sun, as well as the planets, rotates on its axis, and different portions of the surface rotate at slightly different rates. The average period of the rotation of the Sun on its axis is about 26 days. The Sun is a variable star with a twofold variation. One is of long period during the 11-year sunspot cycle, with a range of from 3 to 5%. The other is a short irregular variation with a period of a few days, weeks, or months, and a range of from 3 to 10%. Sunspots are solar cyclones and appear black only by contrast with their hotter and brighter surroundings. They come in 11-year cycles approximately, with periods of maximum and minimum appearance. The brightness and blue color of the sky is due to the scattering of sunlight by the molecules of oxygen and nitrogen in the Earth's upper atmosphere. If there were no atmosphere, the skies would appear black, except in the direction of the heavenly bodies, which would be visible by day as well as by night. The solar corona is the rare outer envelope of the Sun, and it is visible only during a total eclipse of the Sun. It is partly of an electrical nature, and it varies in form during the sunspot cycle. It often extends to a distance of several solar diameters on either side of the Sun. The warmth and the habitability of the Earth's surface is due to the presence of water vapor and carbon dioxide in the atmosphere. Without these substances in the atmosphere, life on the Earth's surface would be impossible. Half of the Earth's atmosphere and all clouds lie within 7 miles of the Earth's surface, and at high elevations above the Earth, the temperature is many degrees below zero. The temperature of space approaches the absolute zero of negative 459 degrees Fahrenheit. The only planets in the solar system, with the exception of the Earth, that might possibly support life are Venus and Mars. Stars shine by their own light, but planets shine only by reflected light from the Sun. If the Earth were represented by a 6-inch school globe, the Sun would be on the same scale a globe 54 feet in diameter. Mercury would be a small ball, 2 1/3 inches in diameter. Venus would be another 6-inch globe. Mars would be a ball about the size of a baseball, 3 1/5 inches in diameter. The Moon would be about the size of a golf ball, 1 1/2 inches in diameter. The largest asteroids would be the size of marbles. Average-sized asteroids would be the size of shot, and the smallest would be merely grains of sand. Jupiter would be a huge globe, standing as tall as a man, 5 feet 6 inches in height. Saturn would be a smaller globe 4.5 feet in diameter, and its ring system would extend to a distance of 5.5 feet on either side of the globe. Uranus would be represented by a globe almost exactly 2 feet in diameter, and Neptune would be a slightly larger globe with a diameter of 2 feet 2.5 inches. The satellites of the outer planets would range in size from tennis and golf balls for the largest to marbles for the smaller and grains of sand for the smallest. On the same scale of measurement, the distance of the 6-inch globe of the Earth from the 54-foot globe representing the Sun would be 1 1/10 miles. The Moon would be placed 15 feet from the Earth globe, and the diameter of the solar system on the same scale, measured across the orbit of Neptune, would be 66 miles. The nearest star on this scale would be 300,000 miles away. If the distance from the Earth to the Sun is taken as 1 inch, so that the scale of the universe is reduced 6 trillion times, the diameter of the solar system across Neptune's orbit is 5 feet, and the distance of 1 light year comes out almost exactly equal to 1 mile. The nearest star to the 5-foot solar system would be 4 1/3 miles away. The most distant known object would be 220,000 miles away, and the extent of the visible universe would be 300,000 miles. On the same scale, the diameter of our Sun would be about 1/100th of an inch, and the diameters of the giant stars Antares and Betelgeuse would be 4 inches and 2 3/4 inches respectively. To see the Earth, we would need a microscope. And with that description of the incomprehensible distances of just our one galaxy, we have reached the conclusion of Astronomy for Young Folks, a most marvelous summary of the astronomical sciences as they existed in 1922. Miss Lewis died in 1966, well within the space race. I can only imagine what she thought, going from a time when we didn't know other galaxies existed to watching rockets take off to the stars. I loved reading this work to you, and I hope you enjoyed it as well. If you'd like to read this work for yourself and see the many illustrations, as always, you'll find a link to a free ebook from Project Gutenberg in the show description. If you'd like to connect, suggest a boring book you'd like to hear read, or request more from one we've already started, you can drop me an email via our website, www.boringbookspod.com. It's always a pleasure to hear from you. Thank you so much for joining me for this evening's reading. Until our next boring book, good night.